So in case you're wondering what's funny about this room, so the seats have been magically rearranged in the last 10 minutes to create 2 aisles instead of 1. I see people are still coming in, but we should get started anyway. So we'll continue the algorithms session, and the next talk is by Francois Le Gall from University of Tokyo, and he's going to talk about an improved quantum algorithm for finding triangles in graphs.
Okay, thank you. So in this talk we'll consider. Is it okay? Okay. So in this talk we will consider the following problem. So we are given a graph, unweighted and undirected, and we want to decide if it contains a triangle or not. So triangle means 3 vertices u, v, w, which are all connected. So for example, the graph on the left has a triangle, so u, v, w, and the graph on the right has no triangle. So why is this problem interesting and important? First, because it has many algorithmic applications. So triangle finding is related to many graph theoretic problems, but also to problems from outside graph theory. So for example, Boolean matrix multiplication, the threesome problem, or designing exact algorithm for max-2 set. A second reason is that triangle finding is one of the most elementary graph theoretic problems for which we don't know precisely the query complexity, especially in the quantum setting. And the third reason is that historically the study of triangle finding has led to the development of several quantum techniques, and indeed historically triangle finding has been a showcase for new quantum techniques. And so how to solve this problem? So classically you can solve this problem in cubic time simply by trying all triples of vertices. So in this talk, n here will always refer to the number of vertices in the graph. And the best known classical algorithm has complexity n to the 2.38 and is based on a reduction to matrix multiplication. So now in the quantum setting we can do much better. You can use quantum search, or Grover search over triples of vertices, and obtain an exponent 1.5. So quadratic speedup with respect to the trivial classical algorithm. But in this talk, we are not really interested in the time complexity, but in the query complexity. That means we want to understand the number of queries of the form is v1, v2, and h needed to solve the problem. So the difference between query complexity and time complexity is the query complexity counts only the number of queries made. So in this case, the number of queries to the adjacency matrix of the graph, while the time complexity counts the total number of operations. And obviously, we can solve triangle finding using n square queries, because with n square queries, you can query all pairs of vertices of the graph, and then you get all the adjacency matrix, so you can then check if it has a triangle without any further queries. And actually this upper bound is tight in the classical setting. It's easy to show that any classical algorithm for triangle finding require omega n square queries. But the same simple arguments only give a linear lower bound for the quantum query complexity of triangle finding, and this is still the best known lower bound. So up to this point, we show that the query complexity of a triangle finding is lower bounded by n, and we have a trivial quantum search algorithm which achieves exponent 1.5. And actually you can do much better. So Magnès, Santa, and Szegedi have shown how to achieve exponent 1.3 using the technique known as the quantum walks. And interestingly, so their algorithm also solves weighted version of triangle finding with the same complexity. So for example, the problem of finding 3 vertices such that the sum of the weights of the 3 edges is equal to 0. Okay? And then there have been a further improvement using another technique known as learning graph. So first, the complexity has been decreased to 35 over 27, and then 9 over 7. And this 9 over 7 exponent has also been obtained by using a generalization of quantum walks. Okay, and recently a lower bound has been shown. So Beloff and Rosmanis have shown that any quantum algorithm based on non-adaptive learning graphs, like these 2 algorithms, or any quantum algorithms also solving weighted versions of triangular finding, like this algorithm, must use essentially n to the 9/7 queries. This means that if you restrict yourself to non-adaptive learning graph, you cannot do better than 9/7. And what we show that we can do better. We obtain a quantum algorithm with query complexity n to the 5/4, where the tilde notation here means that we are omitting polylog factors. Okay? And of course, our algorithm, our quantum algorithm, does not use non-adaptive learning graph because we have a lower bound for this approach. It doesn't use learning graph at all. Instead, it uses combinatorial properties of unweighted graphs and standard quantum walks. And besides breaking this 9/7 barrier, I think this result is interesting because it proves that in the quantum query complexity setting, unweighted triangular finding is easier than its weighted version. Okay, because for the weighted version, we have this lower bound. But it's not really surprising because results strongly suggesting similar separations are known in the classical time complexity setting as well. But in the time complexity setting, of course, we don't know how to prove interesting lower bounds. So these classical lower bounds are conditional, assuming, for example, the complexity, the hardness of solving the three-sum problems. But the separation we obtain in the quantum query complexity setting is unconditional. Okay, so now I will move to the technical part of this talk, and I will start with an overview of the concept of quantum walks, especially for graph problems. So typically, we want to solve this kind of problem. We want to find a marked M subset B of the set of vertices V, okay, where M subset simply means a subset of size M, so M is some parameter, and marked means satisfying some condition. For example, containing an edge of a triangle. And the first thing that we can try to do to solve this problem is to use classical random sampling. So you take a random M subset, you check if it is marked, and if not, you take another subset, and again, you repeat this. And the number of repetition until finding a solution will be 1/epsilon, where epsilon is a fraction of marked subset. Okay? And for each sample, you will need to check whether it is marked or not. So the overall complexity will be 1/epsilon times C, where C is the cost of checking if one subset is marked. So now you can use, you can do better by using Grover search, or more precisely amplitude amplification. You can obtain a quadratic speedup for the first term here. Another way of solving this problem is to use quantum walks. So quantum walk search over the Johnson graph. So the Johnson graph is a graph where each node represents an M subset. Okay, and a quantum walk is a quantum version of random walk. So a random walk on the Johnson graph will start with an initial node of the graph, check if it is marked, and if not, we'll move to a randomly chosen adjacent matrix, adjacent vertex. Check if it is marked, and if not, move again to an adjacent vertex chosen at random. And the quantum walk will be a quantum version of that. That is, instead of moving to a randomly chosen adjacent node, we will move to a we will move to a quantum superposition of the adjacent nodes. Okay? And the key idea is the quantum walk search is to perform the quantum walk while keeping a data structure for the visited node, the visiting M subset. So for instance, the data structure can be the adjacency matrix of the graph induced by the subset corresponding to the visited node. And the complexity of such a quantum walk search is given by this formula. The point is that we are working with a data structure, so we need to maintain the data structure. So for example, you need to construct the data structure of the initial node of the Johnson graph. And this cost is represented by S, the setup cost. And you need also to update the data structure when we are moving to a superposition of the adjacent vertices. And the cost is represented by U here. And C will represent the checking cost. But the cost of checking if B is marked given the data structure. Okay? And the point is that the data structure will typically record relevant information about the problem, about the graph, so it will be easier to check if B is marked when you have the data structure. So this cost C will be typically smaller than the cost C in the Grover search where there is no database. Okay? This is why quantum walk search can be faster than Grover search. But of course, we have to consider the additional cost, S and U. So this quantum walk search can be only faster if S and U are low enough. Okay? So now I will describe the main combinatorial arguments behind our algorithm. And I will use this graph as a running example. The first thing that we do is we take a random set large X of about square root n vertices. So for example, here I will take this set of two vertices, x1 and x2. And then we will check if the graph contains a triangle with a vertex in large X, simply by performing a Grover search over the triples of vertices containing one vertex in large X. So the complexity will be given by these formulas. It's n to the 5/4. And now what's happened if no triangle has been found? Okay? When no triangle has been found, we know that for each vertex u in large X, there is no edge of the triangle in the neighborhood of u. Okay, why? Because if there were some edge in the neighborhood, it will form a triangle, and this triangle would have been found at step 1. So for example, here we know that there is no edge in the neighborhood nx1 and no edge in the neighborhood nx2 here. Okay, so what remains to do is to check if there exists a triangle with an edge in this set. So the set of pairs of vertices which are not in a neighborhood of a vertex in large X. So again, the set of pairs of vertices which are not in a neighborhood of a vertex in large X. Okay? And we have a key property which is easy to show. It's that for each pair of vertices uv in this set, there are with high probability on the choice of large X at most square root n vertices w which are connected to both u and v. So for example, here, there are at most square root n vertices connected to these two vertices. Why? Because if it is not the case, if there are more than square root n vertices, then with high probability, uv will be put in S. Okay? And this key property leads, well, it's from a simple, straightforward counting argument. This key property implies the following inequality. So the sum of the size of this set is upper bounded by n to the 2.5. The important thing here is that the trivial upper bound on this sum is n cubed. This means that this key properties imply the sparsity for these sets. And the precise value here, the exponent 2.5, depends on the size of large X, and we choose square root n here, giving n to the 2.5, because square root n is the optimal value for this strategy, will be the optimal value for this strategy. Okay, so now how to implement the second step? It's easy to see that implementing this second step is equivalent to checking if there exists a vertex W such that this set contains an edge. Okay, and we can try to implement this by a Grover search. And the complexity of such a Grover search will be given by this formula. And since we have this inequality, this will give you a complexity of a big O of n to the 5/4. Okay, so we would have complexity n to the 5/4 for the first step, the second step, and thus for the complexity of the whole algorithm. But there is a big problem here. To do that, to apply Grover search, we need to know these sets. We need to know the sets over which we are doing a Grover search. And these sets are very complicated to construct. So for example, computing S requires n to the 1.5 queries, which is too much. And computing each neighborhood requires a linear number of queries, which is too much. So this means that we cannot use this implementation because we don't know how to construct this set efficiently. And I should notice that similar sparsity arguments have been used in prior work. So for example, in classical combinatorial algorithm for Boolean matrix multiplication, and also the quantum combinatorial algorithm for triangle finding by Magnès, Santa, and Szegedy. And all these prior works have the same problem, so they reduce the problem to some search over some sparse sets, but the problem was that it was unclear how to construct efficiently these sparse sets. And what we show that for this specific strategy, and in the quantum query complexity setting, step 2 can be implemented using quantum walk without completely constructing these sets, so that we can obtain actually the same complexity here without constructing explicitly all these sets. So this is the main technical contribution of this work. So how do we do this? So remember, the current approach for step 2 is the following two-level search. You check if there exists W and a vertex W such that this set contains an H. And as I said, we have two problems. We don't know how to compute S efficiently, and we don't know how to compute each neighborhood efficiently. And the key is to introduce an intermediate search step. So we will do as before. We'll check if there exists W, but then we will check if there exists a subset B of the set of vertices of psi square root n, such that the same thing as before, but now restricted to B. And it's easy to see that the two approaches are checking the same thing, but they are checking the same thing in different ways. And the point is that we can implement the second step using a quantum walk, and if we choose as a database this set, NW intersect B, then at the last step, the final step of the algorithm, we know this set because it is in the memory of the walk, memory of the algorithm. Okay, so this solves completely problem 2, computing these neighborhoods. But of course, problem 1 remains, how to compute the right part here. And this can be solved by introducing another level in the algorithm. So the first level here, you will start by checking if there exists a subset A of size n to the 3/4, such that, as before, there exists W, there exists B, but this time B is taken in large A, and finally the final checking condition. And we implement the first one again using a quantum walk, and as data structure, we choose S intersect A times A. And if you do this, then you know this set at the end, at the last step of the algorithm, because this set is in the data structure. It's a subset of S intersect A times A. So this completely solves problem 1, 2. Okay? So the conclusion is that at the last, if we use this strategy, so it's a 4-level quantum algorithm, at the last step here, we know all these sets. So we are in the ideal situation, and we can exploit the sparsity of these sets. And if you work out the query complexity of this algorithm, then you can show that it is upper bounded by n to the 5/4 up to polylogarithmic factors. So the derivation of this upper bound is quite mechanical. We have to upper bound the setup cost, the update cost, the checking cost of the two quantum walks. And for example, I will just give one example. So the setup cost of the first walk, it is the cost of creating the database associated to A for some given A. It's easy to see that, well, if you remember the definition of S, that it is upper bounded by the size of X times the size of A, which is n to the 5/4. That's why we choose actually this parameter here, to keep this complexity smaller than this. Okay? But there is a significant technical difficulty. It is that this approach works, this analysis works, if all these sets are sparse. But what we know about the sparsity of the graph is this inequality. So we have only a global sparsity condition on the graph. So we know that this inequality holds, but it doesn't imply that the sparsity holds for each of these sets. This only implies that the sparsity holds for large fractions of these sets. And it's quite problematic, because when analyzing quantum walks, you really need an upper bound on the worst case complexity of the checking cost of the walk. And we don't have it. We don't have this guarantee if these sets are not sparse. But actually, we can overcome this difficulty by carefully redefining the second walk here, and replacing the Grover search here by Grover search with variable checking costs. And if you do this, well, the analysis of the complexity becomes much more involved, but we can still show that it's upper bounded, the final complexity is upper bounded by n to the 5/4 up to polylog factors. Okay? So to summarize what we have done, so we had a high-level strategy, so to which we are checking if the graph has a triangle in 2 steps. The first step using Grover search, and the second step exploiting the sparsity of these sets. And we observe that if we know these sets, then we can implement step 2 directly using Grover search, but we don't know how to construct this set efficiently. But we have shown that instead, we can overcome this difficulty and we can implement step 2 with essentially the same complexity, so n to the 5/4 queries up to polylog factor, by replacing this Grover search by our 4-level quantum algorithm. And the main idea was to perform the constructions of the relevant part of these sets on the fly, concurrently to the search by using quantum walks. Okay? So, as a conclusion, our main result is a new quantum algorithm for unweighted triangular finding with a complexity n to the 5/4 up to polylog factors. And in particular, this shows that n to the 9/7 is not the lower bound for this problem. So currently, what we know about the quantum query complexity of unweighted triangular finding is that it is between n and n to the 5/4. Okay, thank you.
Okay, time for a question. So if there's no question, then I have a complaint.
Yeah.
So I actually lost a bet about a bottle of wine a while ago because I thought the complexity of triangle finding should be 9/7. But then your paper came along and I lost the bet. Yeah.
Thank you.
So let's say if I ever have a bet about this again, what should I bet for?
Oh, so you're asking for the complexity of query complexity. So I don't know, but I would be quite surprised if it were n, because it seems a very complicated algorithmic problem. So I would be very surprised if you can do it with n queries. But I don't have any evidence of that. It's only my intuition.
I see. But do you think this sequence might continue a little bit further? Like, are there sort of unexplored directions in your argument that could be improved?
Yes, so the point is that, so my argument, so in the ideal situation where everything is known here, then this approach cannot give anything better than n to the 5/4. Because all the 4-level quantum algorithm is only here in order to overcome the difficulty that we don't know this. And even if you do know this thing, you cannot obtain something better than n to the 5/4 for this approach. So you really need another combinatorial argument. But it's possible that it exists. But it really would require new ideas and new insight into the nature of the problem.
Okay, thank you very much. Where's John?